Picture this, it's 9 a.m. A developer opens their AI assistant and types the first prompt, design the base schema for this feature. They wait. They review. They copy the output, paste it in the next prompt, now write the API endpoints for that schema. Wait again. Review again. Then, write the unit tests for those endpoints. Fix the test that failed. Then update the README. 8 hours later, they are still manually chaining prompts, acting as the glue between AI responses that have no awareness of each other. Every context switch costs them focus. Every handoff loses information. This is the single agent trap, and most developers don't even realize they are in it, because this is simply how AI-assisted development has always worked. But what if a coordinated team of agents could handle that entire pipeline autonomously in under 30 minutes while you review the final result? That is exactly what you will build by the end of this lecture. So here is the concrete promise of this lecture. By the time we reach the final chapter, you will have configured a full team mode pipeline using oh-my-claudecode, OMC for short. This pipeline will autonomously plan a feature, write the implementation, execute verification steps, catch failures, and self-correct. Without you writing a single intermediary prompt, you are not learning a new programming language. You are not configuring a complex orchestration framework from scratch. You are commanding a coordinated team of specialized AI agents using plain natural language. The pipeline does the coordination. You define the goal. And the question you should be asking right now is, what exactly is OMC, and how does it make this possible? That answer is coming in the next 90 seconds. Let's be precise about what oh-my-claudecode is, because the name can mislead you. OMC is not a new AI model. It is not a fork of Claude. It is not a standalone application you install instead of something else. OMC is a multi-agent orchestration layer that sits on top of Claude Code, Anthropic's terminal native assistant. Think of Claude Code as a single highly skilled engineer. OMC is the project management system that lets you deploy a team of those engineers, assign them specialized roles, define how they communicate, and coordinate their outputs into a single coherent result. The underlying intelligence is still Claude, but the coordination, the role assignment, the inter-agent communication protocol, that is what OMC provides. This distinction matters because it means OMC's capabilities scale with Claude's capabilities. Every improvement Anthropic ships to Claude Code is automatically inherited by your OMC pipeline. But wait, if it is just a coordination layer, how hard is it to set up? Simpler than you think, and we will prove that in the next chapter. Now let's put OMC head-to-head against the traditional single AI workflow, so the difference is impossible to ignore. In the traditional approach, you have one AI, one context window, one response at a time. You manually orchestrate, meaning you are the one deciding what to ask next, what output to pass forward, and what to do when something breaks. The cognitive load is entirely on you. With OMC, you issue a single natural language instruction, something as simple as implement the user authentication feature with tests, and a team of specialized agents takes over. A planner agent decomposes the goal, a coder agent implements it, a test agent validates it, a fixer agent handles failures. And critically, OMC requires zero new syntax. No YAML pipelines, no DSL, no configuration schemas to memorize. If you can describe a task in plain English, you can command an OMC agent team. The barrier to entry is essentially zero, and the productivity delta is enormous. In the next chapter, we will install OMC and prove this claim under 5 minutes on a live project, so stay with us. Let's get OMC running. The fastest path is the Claude Code Marketplace. Open Claude Code, hit the plugins panel, search for OMC, and click install. That's literally it. No config files to touch, no environment variables to set. The Marketplace plugin bundles a sane default configuration that works for 80% of projects out of the box. Under the hood, it pulls the oh-my-claude Sisyphus package and wires up the agent communication layer automatically. One thing to note, the Marketplace installs your OMC version to Claude Code's update cycle, which means you always get a tested, compatible build. If you're onboarding a team and want everyone on the same version without managing package JSON entries, this is your path. But, and this is the part most devs miss, the Marketplace path has one hard limitation we'll expose in the very next scene. Here's when you skip the Marketplace and go straight to NPM. If you're working in a CI/CD pipeline, a Docker container, a remote dev environment, or any headless setup where Claude's GUI isn't in the picture, NPM is your only option. Run pm install oh-my-claude Sisyphus. The package name is a mouthful, but it's intentional. Sisyphus is a reference to the iterative agent loop at the core of OMC's design. After the global install, you also get the OMC CLI binary available system-wide. For monorepos or projects where you want to pin the exact version per workspace, drop the G flag and install it locally, then add it to your scripts block. The npm path also gives you access to pre-release builds by appending it next to the package name. Useful if you want features that haven't landed in the marketplace yet. The trade-off: you own the update responsibility. Now let's see how these two paths actually stack up against each other. But let's put both paths side by side so the decision is obvious. Marketplace wins on setup speed. It's a single click with zero terminal work. NPM wins on environment flexibility. It works anywhere Node.js runs. For update management, Marketplace is automatic, but you're on CloudCode schedule. NPM is manual, but you control the exact version. Here's the surprising one: environment flexibility. Marketplace only works inside the CloudCode GUI. The moment you step outside that boundary, a GitHub Actions runner, a code space terminal, a remote SSH session, Marketplace doesn't exist. NPM is your only path. My recommendation: use Marketplace for local development on your own machine. Use NPM for anything that touches automated infrastructure. Coming up next, we'll run the setup command and watch OMC scaffold your entire agent workspace in seconds. Once OMC is installed, the next command you type is setup, and it does a lot more than most init commands. Navigate to your project root and type setup in the Cloud Chat panel, or run OMC setup from the terminal. OMC immediately reads your project structure, detects your language and framework, and makes opinionated decisions about which agent roles make sense for your codebase. It creates 3 key files: omc.config.json, which defines your pipeline stages and agent roles; OMC skills, a directory where agent capability definitions live; and OMC pipeline.json, which is the wiring diagram connecting agents to tasks. Each file has a clear purpose. omc.config.json is the one you'll edit most. It's where you define which agents participate in which stages. But here's what's interesting: OMC ships with 5 pre-built agent personas baked into default scaffold, and most developers never realize they'd be customized. We'll dig into that structure right now. Here's what your workspace looks like after setup completes. The OMC directory is the brain of the operation. Inside skills, you'll find files like architect.skill.json, coder.keys.json, reviewer.skill.json, tester.json, and documenter.json, 5 agents, each with a dist role definition, capability scope, and communication protocol. The pipeline.json maps task types to agent sequences. A feature request routes through architect, then coder, then reviewer. A bug fix skips architect and goes straight to coder, then tester. This is the multi-agent routing logic that replaces the single agent trap we talked about in Chapter 1. The omc.config.json at the root is where you control the macro behavior. You can disable agent reorder stages or inject custom personas. One critical detail: all of these files are committed to version control. That means your entire agent team configuration travels with your repo. Your teammates get the exact same agent setup without running setup again. Next, we'll confirm everything is actually working, because a misconfigured install can silently fail in ways that are frustrating to debug. Before you build anything with OMC, you need to confirm the installation is actually healthy, not just present. Run OMC health from the terminal. It checks 5 things in sequence: that the OMC binary is reachable on your package, that the config files are valid.json, that the agent communication layer can initialize, that your Claude API key is accessible to the runtime, and that at least one skill definition is loadable. Each check either passes with a green tick or fails with an error code. The error codes are specific enough to tell you exactly what's wrong without guessing. Beyond the health command, check that the directory exists in your project root, and that pipeline.json is not empty. If you installed via Marketplace, also confirm the OMC plugin shows as active in the CloudCode plugins panel. Installed and active are 2 different states, and only active means the agent layer is running. A clean health check means you're ready to run your first multi-agent pipeline. But most new users hit one of 3 specific errors first. 3 errors account for 90% of failed OMC installs. Let's kill them before they kill your momentum. First, agent layer failed to initialize. This almost always means your Anthropic API key environment variable is missing or set in the wrong scope. Fix: export it in your shell profile, not just in the current terminal session. Second, pipeline.json parse error. This happens when setup was interrupted mid-run, leaving a malformed file. Fix: delete OMC directory and rerun setup cleanly. Third, OMC command not found after a global npm install. This is a patch issue. Your npm global bin directory isn't in your patch. Fix: run npm config get prefix, take that path, append bin, and add it to your patch in bash or .xc. These 3 fixes resolve virtually every fresh install failure. Now here's what's waiting in the next chapter. We'll take this working OMC installation and build your first actual multi-agent pipeline, a team mode workflow where architect, coder, and reviewer agents pass work to each other automatically. That's where the real productivity shift happens. Here's the reality most developers hit when they first try AI coding tools. They get a single response, a single file, maybe a single function, and then they're back on their own, stitching it all together manually. Team mode in OMC is built to destroy that bottleneck entirely. Instead of one agent doing one job, team mode chains 5 specialized agents into a sequential pipeline: team plan, team PRD, team exec, team verifix. Each stage consumes the output of the previous one automatically. No copy-paste. No manual handoff. You give it a natural language task at the top, and a verified, working implementation comes out the bottom. Think of it like a miniature software team running at machine speed. The architectural insight here is that each stage has a narrow, well-defined contract, which is exactly why the whole pipeline is reliable. But the real question is, what actually happens inside each of those 5 stages? Let's break every one of them open. The first stage, team plan, is where the magic of structure begins. You hand OMC a raw, natural language feature request, something like add a paginated user search endpoint with role-based filtering. Most tools would just try to write that code directly and produce something half-baked. Team plan does something fundamentally different. It runs a dedicated planning agent whose only job is decomposition. It asks, what are the discrete tasks here? What are the dependencies between them? What context from the existing codebase is relevant? The output is not code, it's a structured task specification, essentially a machine-readable project plan. This is critically important because it forces ambiguity out of the system before any code is written. Vague input gets clarified at the planning layer, not discovered as a bug 3 stages later. And here's a detail that surprises most developers. The planning agent actually reads your existing file structure and open files to ground its plan in your real codebase. It's not planning in a vacuum. So by the time team plan finishes, you already have a blueprint that a human tech lead would be proud to sign off on. Next, that blueprint gets transformed into something even more powerful. Once team plan has produced its structured task specification, team party picks it up and elevates it into something that every downstream agent will treat as ground truth: a formal product requirements document. Now, in a traditional team, this PRD would take a product manager hours, maybe days, to write. OMC's PRD agent generates it in seconds, and it's not a generic template. It pulls the specific acceptance criteria, edge cases, data contracts, and API surface definitions directly from the task spec. Why does this matter so much? Because team exec, the code generation agent, doesn't just get vague instructions. It gets a document with precise inputs, expected outputs, constraints, and success metrics. That specificity is what separates coherent, production-grade code from plausible-looking garbage. Also acts as an audit trail. You can read it, review it, and even edit it before the pipeline continues if you want to inject human judgment at this layer. Think of it as the contract between your intent and the machine's implementation. Without it, you'd be hoping the AI guessed right. With it, you're specifying exactly what right means. And now that the contract is signed, it's time to actually build something. This is the stage most people get excited about, and for good reason. Team exec is where the PRD gets turned real running code. What makes it different from just asking a plain LLM to write code is the source of its instructions. The execution agent doesn't guess at what you want. It reads the PRD as a formal specification. Every function signature, every expected return type, every edge case that was captured upstream is now a direct constraint on what gets generated. Let me give you a concrete example. Say your PRD specifies a paginated search endpoint. Get user search, query paronque, page and limit, returns a JSON array with a total count field, filters by role from JWT claims, and must handle empty result sets without erroring. Team exec generates the route handler, the service layer function, the database query with parameterization, and even the basic error handling, all consistent with each other because they all derive from the same PRD. It so respects your existing code style by reading the surrounding files. The output isn't a suggestion, it's a diff, ready to apply. But generated code and correct code are not the same thing. That's exactly why the next agent exists. Here's where team mode separates itself from every AI coding assistant you've used before. After team exec produces its implementation, team verified doesn't just sit back and assume everything is fine. It acts like a QA engineer who takes the PRD in one hand and the generated code in the other, and checks one against the other systematically. The verification agent runs 3 distinct checks. First, it executes any existing test suite, unit tests, integration tests, and captures the full output including any failures and stack traces. Second, it runs linting and static analysis against your configured rules, flagging type errors, unused imports, and style violations. Third, and this is the clever part, it evaluates the code against the PRD's acceptance criteria directly, checking whether behavior matches the specified behavior, even cases that tests might not cover explicitly. Everything passes, the pipeline marks the stage green and moves on. If anything fails, Team Verify generates a structured failure report, not just an error dump, but a categorized, Prioritize list of issues with references back to the specific PRD criteria that were violated. Report is the exact input that the final stage needs. And that final stage is self-healing magic happens. Team Fix is the stage that makes the whole pipeline genuinely autonomous. When Team Verify produces a failure report, Team Fix reads that structured document, not the raw error output, but the categorized PRD rinsed report, and generates targeted patches for each identified issue. This is fundamentally different from rerunning the whole execution stage. Team Fix has surgical precision. It knows exactly which lines produced which failures, which acceptance criteria were violated, and what the expected behavior was supposed to be. It applies minimal, focused changes rather than regenerating entire files. After patching, the pipeline loops back to Team Verify automatically. This Verify Fix loop can iterate multiple times until either all checks pass or a maximum retry threshold is reached, at which point OMC surfaces the remaining issues for human review rather than silently failing. In practice, most common implementation bugs, off-by-one errors, missing null checks, incorrect response shapes, are resolved in the first fix iteration without any developer involvement. What you're left is not just generated code, it's generated, tested, and self-corrected code. That is the definition of a self-healing pipeline. Now that you understand all 5 stages theoretically, it's time to run one for real and watch exactly what happens. Alright, theory is over, let's run it. Open your terminal in a project that OMC is already initialized in. The command to trigger the full team mode pipeline is straightforward. You call amteam with the run subcommand, followed by your task description in quotes. Here's the exact command: OMC team run add a Git user's search endpoint with pagination, query filtering by name, and role-based access control using JJWT claims. Hit enter and watch what happens. First, you'll see team plan activate. OMC prints each subtask it identifies in real time. You'll see it list things like define route handler, create service function, write repository query, add JWT middleware check. Then team party fires, and you'll see it output the path to the generated PRD file. You can open that file right now and read it while the pipeline continues. Then team exec starts generating. You'll see file paths appearing as each file is written. Then team verify runs your test suite live in the terminal. If there are failures, team fix kicks in automatically. You'll see applying patch for failure, missing null check on query param message, and then the loop closes. Total wall clock time for this example on a mid-tier laptop, around 45 seconds. One command, 5 stages, a working verified endpoint. But let's not just celebrate, let's look at exactly what was produced. Let's map the artifacts back to the stages that produced them, because this is where the pipeline's value becomes tangible. Inside your project after a successful run, you'll find 3 categories of output. First, under the OMC directory, you have the PRD markdown file from Team PRD, and every acceptance criterion listed, every data contract defined. This is your audit trail. Second, in your source tree, you have the implementation files from Team Exec, in this example, a new route file, a service layer module, and a repository query function, each one coherent with the others, because they all derived from the same PRD. Third, also in your source tree, you have generated test files from Team Exec and test results from Team Verify showing all green. The documentation didn't cost you extra. It came out of the pipeline as a natural artifact of stage 2. The tests didn't cost you a separate prompt. They came from the execution agent reading the acceptance criteria. Every piece traces back to a specific stage with a specific input. This traceability is what makes team mode trustworthy, not just impressive. Now, knowing all of this, when should you actually reach for team mode versus something lighter? Team mode is powerful, but it's not the right tool for every job, and knowing when not to use it is just as important as knowing how to run it. Team mode delivers the highest return when you're building a complete, well-scoped feature from scratch, something with clear inputs, outputs, and acceptance criteria. New API endpoints, data migration scripts, standalone modules, these are ideal. It's also the right choice when you want that self-healing loop to handle an ambiguous bug report, where you're not sure how deep the fix goes. On the other hand, if you're making a small targeted change, renaming a function, adjusting a single config value, tweaking a CSS class, team mode is overkill. The pipeline overhead will cost you more time than just editing the file manually. Similarly, if your task involves highly exploratory, research-oriented work with no defined success criteria, Team PRD will struggle to generate a meaningful PRD and every downstream suffers. For those cases, OMC has lighter orchestration modes, and that's exactly what we're going into next. In the next chapter, we're going to look at advanced orchestration modes, including parallel execution, where multiple agents run simultaneously across independent tasks, cutting pipeline time by a factor you probably won't believe until you see the benchmark. Here is the part most developers completely miss. OMC doesn't have one way to run agents. It has 5 distinct orchestration modes, and picking the wrong one is the difference between a workflow that finishes in 2 minutes and one that stalls for 20. The 5 modes are Team, Autopilot, UltraWork, Ralph, and Pipeline. Team is your collaborative baseline. Agents discuss and vote. Pipeline is your sequential assembly line. Autopilot removes the human entirely from the loop. Ralph guarantees completion no matter what. And UltraWork is the nuclear option, maximum parallelism, all agents firing at once. Think of these as gears in a transmission. You wouldn't drive a highway in first gear, and you wouldn't run a safety-critical task in UltraWork without understanding the trade-offs. By the end of this section, you'll know exactly which gear to reach why. Coming up next, we'll see what happens when you hand the wheel entirely to Autopilot. Autopilot mode is exactly what it sounds like. You describe the goal and OMC takes over completely. No approve prompts. No mid-task check-ins. The agent chain runs from start to finish without waiting for you. This is incredibly powerful for well-defined, repeatable tasks. Generating test suites, scaffolding boilerplate, running documentation passes. But here is where developers get nervous, and rightfully so. What stops an autonomous agent from making destructive decisions? OMC's Autopilot has 3 built-in guardrails. First, a dry run scope check that maps every file and API and task intends to touch before execution starts. Second, a rollback snapshot. The full state is saved before any write operation. Third, a confidence threshold. If any subagent scores below the configured confidence level, it escalates rather than proceeding. So Autopilot is not reckless autonomy. It is guarded autonomy. The critical question is, what happens when a task is not just autonomous but also prone to failure? That is exactly what Ralph mode was designed to solve. Ralph mode solves a specific and painful problem. Tasks that fail partway through and leave your codebase in a broken intermediate state. We have all been there. An agent writes 3 files, the 4th call times out, and now you have half migrated code with no clean path forward. Ralph introduces a completion guarantee loop. When a subtask fails, Ralph does not just retry it blindly. It first analyzes the failure reason. Was it a timeout, a logic error, or a dependency issue? It then reroutes. If the original agent cannot solve it within 2 retries, the task is handed off to a backup specialist agent. Only after a verified output is confirmed does Ralph mark the task complete and advance the pipeline. Think of Ralph as a persistent senior engineer who refuses to close a ticket until the work actually passes review. The guarantee is not infinite retries, it is intelligent rerouting until a verified result exists. And when you pair Ralph with UltraWork's parallel execution, the performance gains become extraordinary, which is exactly what the next section covers. UltraWork is the mode that makes developers stop and stare. While every other orchestration mode runs tasks in some form of sequence, even team mode, which deliberates before acting, UltraWork decomposes a goal into the maximum number of independent subtasks possible and fires them all simultaneously. Not queued, not staggered. Simultaneously. The architecture behind this is a task dependency graph. OMC first builds a directed acyclic graph of all subtasks, identifies which ones have 0 dependencies on each other, and dispatches those in a single parallel wave. Dependent tasks wait only for their specific prerequisites, not for the entire batch. In practice, this means a task that would take 12 minutes sequentially can finish in under 3. But here is the part that surprises most people. UltraWork is not just for large projects. Even a mid-sized refactor, say updating API response shapes across 15 controllers, maps cleanly to parallel execution because each controller file is an independent work unit. The question developers immediately ask, how does OMC actually spawn and manage these parallel workers? The answer involves a tool you probably already have installed. And it is not what you expect. As of version 4.4.0, OMC's execution engine is built on Tmux, the terminal multiplexer. This is a deliberate and clever engineering decision. Instead of spawning background processes that are invisible to the developer, OMC creates a named Tmux session and opens 1 pane per worker. You can literally watch each agent working in real time in its own terminal pane. Claude handles 1 pane, Codex handles another, Gemini handles a third, all running concurrently, all visible. The stack works like this. At the top is the OMC orchestrator layer, which owns the task graph and dispatch logic. Below that is the Tmux session manager, which creates and names panes and handles interpane signaling. Below that are the CLI worker adapters, 1 per model, which translate OMC task packets into the specific prompt format each model expects. At the bottom is the result aggregator, which pulls each pane for complete signals and pulls output back into the main context. The beauty of this architecture is debuggability. If one worker stalls, you can attach to its pane directly and inspect what is happening. No black box. And here is the part that changes how you think about multi-model workflows. The coordination layer doesn't care which model is in each pane. You can hot swap Claude for Gemini on any worker slot without changing a single line of pipeline config. Let's walk through a concrete parallel execution flow so the architecture becomes tangible. Task, refactor, authentication, middleware across independent service modules, auth service, user service, and notification service. Step 1, OMC receives the task and runs dependency analysis. It determines all three modules are independent, no shared mutable state, no cross-module imports in scope. A three-worker parallel wave is dispatched. Step 2 opens three panes. Worker 1 gets Claude with the auth service context. Worker 2 gets Codex with the user service context. Worker 3 gets Gemini with the notification service context. All three start executing simultaneously. Step 3, OMC's result aggregator polls each pane at configurable intervals. Default is every 8 seconds. It watches for the completion signal token each adapter injects at the end of a successful run. Step 4, as workers complete, in any order, their outputs are written to a staging buffer. Step 5, once all three completion signals are received, the result merger runs a conflict check, validates output schemas, and writes the final merged result to the working directory. Total wall clock time, the duration of the slowest single worker, not the sum of all three. That is the ultrawork advantage. Next chapter, we will explore how you control the cost of running all these agents. Because parallel power without cost guardrails is a budget disaster waiting to happen. Power users of OMC do not type out full orchestration mode configurations for every task. They use magic keywords, short trigger strings that expand into fully configured pipeline definitions the moment OMC parses them. The four most important ones are Ralph, OL, autopilot, and pipe. Type Ralph before any task description and OMC instantly wraps the entire execution in a Ralph completion guarantee loop. No confound edits required. Type O and you get a full ultrawork decomposition with dependency graph analysis pre-applied. Autopilot triggers the guarded autonomous pipeline with all three safety rails enabled by default. Pipe invokes a clean sequential pipeline mode. The time savings are not trivial. A manually configured Ralph pipeline requires editing the orchestration config, setting retry thresholds, defining the backup agent roster, and specifying the verification gate. That is roughly 4 minutes of setup for an experienced developer. The Ralph magic keyword does all of that in one word. There is also a fifth keyword worth knowing, deepint, short for deep interview, which triggers OMC's structured requirements gathering mode before any execution begins. We will cover deepint in detail in the next chapter, because it is the keyword that separates developers who get mediocre results from those who get production-ready output on the first pass. Behind every magic keyword is a roster of 32 specialized agents that OMC maintains internally. These are not generic AI instances. Each one is a role-configured specialist with a tailored system prompt, a defined tool access scope, and a performance profile optimized for its domain. The roster breaks into 5 domains. Architecture agents handle system design decisions, dependency evaluation, and module boundary definitions. Testing agents own unit test generation, integration test scaffolding, and coverage gap analysis. Design agents produce UI component specs, design token suggestions, and accessibility audits. Documentation agents write API docs, inline comments, and README structures. Security agents run static analysis, dependency vulnerability checks, and secret scanning. The remaining agents cover deployment, performance profiling, database schema design, and more. What is critical to understand is that you rarely interact with these agents by name. OMC's dispatcher reads your task description and routes automatically. You write add input validation to the user registration endpoint. OMC routes that to the security agent and the testing agent in combination, not generic coder. That routing intelligence is what we will unpack next. The dispatcher is the hidden engine that makes the 32 agent roster actually useful. Without smart routing, you would need to manually specify which agent handles each task, and that defeats the purpose of having specialists. OMC's dispatcher works in 3 steps. First, it runs a semantic classification pass on your task description using an intent taxonomy it maintains internally. Roughly 80 task intent categories map to agent roles. Second, it scores each candidate agent against the task using a weighted feature match, verb type, noun domain, output format requirement, and risk level. Third, it resolves multi-agent tasks that span 2 or more domains, by creating a micro pipeline on the fly, assigning a lead agent and 1 or more contributing agents. So when you write refactor the payment gateway and add test coverage, the dispatcher doesn't route that to a single agent. It creates a 2-agent pipeline. Architecture agent leads the refactor, testing agent contributes coverage in parallel. The routing decision is made in under 200 milliseconds and logged. You can inspect every dispatch decision in OMC's trace output. In the next chapter, we will go deeper on cost control strategies and the deep interview mode, the two levers that give you precision control over both quality and budget when running workflows at this scale. Here is a problem most teams hit after their first week with AI agents. Every task, regardless of complexity, gets routed to the most powerful and most expensive model available. Summarizing a README, full opus pricing. Renaming a variable, full opus pricing. OMC solves this with a smart routing layer that sits between your task queue and the model endpoints. Lightweight, deterministic tasks, file reads, code formatting, simple lookups, get routed to Haiku, which costs roughly 1/20th of opus per token. Only tasks requiring multi-step reasoning, architectural decisions, or ambiguous problem-solving get escalated to opus. The routing decision happens automatically based on task complexity signals OMC extracts from the prompt and context window size. Think of it as a load balancer, but for intelligence. And the savings are not marginal. We are talking 30 to 50% reduction in total token spend for a typical development workflow. Stay with me because the actual numbers will surprise you. Let us put real numbers on this. Imagine a developer running a typical day of agent tasks. 40% of tasks are simple, reading files, formatting output, echoing summaries. 5% are medium complexity, generating unit tests, extracting types, writing docstrings, and 25% are genuinely hard, designing module interfaces, debugging race conditions, refactoring cross-cutting concerns. Without smart routing, every single one of those hits opus pricing. With OMC's routing, the simple and medium tiers drop to Haiku, and only the hard tier stays on opus. The table you see now shows the per-task token cost at each tier, the naive single-model total, and the routed total. The result is consistent. Across benchmarks, routed usage runs 35 to 48% cheaper than naive single-model usage for the same output quality. The quality gap on Haiku-eligible tasks? Negligible, because those tasks do not need deep reasoning in the first place. But the routing rules themselves are configurable, which is exactly what the next scene covers. The default routing heuristics work well out of the box, but OMC gives direct control over the thresholds. You can push more tasks toward Haiku if cost is the priority, or pull more toward opus if output quality is non-negotiable for your domain. These are the key configuration knobs you need to know. Set them once in your OMC config file, and they apply globally across all agent sessions, no per-task annotation required. And if you have tasks that should never touch a cheaper model, security audits, compliance checks, anything where a wrong answer has real consequences, you can hardpin those task types to opus regardless of complexity scoring. Coming up next, a feature that is completely unrelated to cost, but dramatically changes how much rework you do, the deep interview command. Every developer has written a vague prompt and gotten back code that technically answered the question, but completely missed the actual need. The problem is not the model, it is the specification. Garbage in, garbage out, and the garbage happens before the first token is generated. OMC's deep interview command exists to break this cycle. When you prefix a task with deep interview, OMC does not immediately start generating code. Instead, it enters a structured Socratic questioning mode. It identifies ambiguities in your prompt, surfaces assumptions it would otherwise have to guess at, and asks you a sequence of targeted clarifying questions, one at a time, not as a wall of text. The questions follow a logical dependency chain, high-level goals first, then constraints, then edge cases. This mirrors how a senior engineer would interview a product manager before touching a keyboard. The sequence typically runs 3 to 7 questions. By the end, OMC has a structured requirements model it carries into the task, not a paraphrased version of your original prompt, but an actual specification. And here is the part that changes your mental model about where defects really come from. Let me show you the concrete difference this makes. Take a common prompt. Build a user authentication system. Without deep interview, OMC makes a dozen silent assumptions, GAWT or sessions, single factor or MFA. What is the password policy? What database schema is already in place? The output code answers those questions one way, but there is a 60% chance it is the wrong way for your actual context. Run the same prompt through deep interview, and what comes back is a requirements document with explicit answers to all of those questions, sourced from you, not guessed by the model. The downstream code accuracy difference is dramatic. On internal benchmarks, tasks initiated with deep interview require 40% fewer follow-up correction prompts and produce modules with half the number of interface mismatches compared to direct prompting. The side-by-side comparison on screen right now captures exactly this delta. The key insight: the cost of 7 clarifying questions is always less than the cost of 3 rounds of rework. And once you have that requirements document, there is a way to make it even more reusable, which is what custom skills are built for. Here is the problem with knowledge in most teams. A senior engineer debugs a gnarly race condition, writes the fix, merges the PR, and that pattern lives in the Git history forever. but no one ever reuses it. The next time a similar bug appears, the wheel gets reinvented. Custom skills in OMC are the solution to this problem. A custom skill is a structured file that encodes a successful debugging, refactoring, or analysis pattern, not just the solution, but the reasoning steps, the context triggers that indicate when to apply it, and the expected output shape. Once you save a custom skill, OMC monitors incoming task descriptions for matching signals. When a new task looks like it fits the pattern, similar file types, similar error signatures, similar structural context, OMC automatics the skill file into the agent's context before the task begins. The agent does not start from scratch. It starts with the accumulated wisdom of every engineer who has solved this class of problem before. The question is, what does that skill file actually look like? A custom skill file is a YAML document with 4 mandatory sections. First, the metadata block, skill name, version, and author. Second, the triggers block, a list of signal patterns, file extensions, error message substrings, task description keywords, any one of which causes OMC to activate this skill. Third, the context block, the actual reasoning steps, heuristics, and reference code the agent receives as injected context. This is where you encode the senior engineer's knowledge. Fourth, the output spec, the expected shape of the agent's response, what fields, what format, what validation criteria. When OMC sees a new task description containing essentio, race condition, or event loop hang, it automaticals the agent's debugging skill and injects the context block into the agent's working memory. The agent now debugs your async code with the benefit of every similar fix your team has ever made. Here is the structure in practice. Pay attention to the triggers section, because that is where most teams underinvest. Here is the long game value of custom skills that most teams miss until they are 6 months in. Each skill your team captures is an asset that compounds. Month 1, you have 3 skills. Month 3, 15. Month 6, your entire OMC setup is dramatically smarter than a fresh install. Not because the model changed, but because you encoded your organization's hard-won knowledge into the system. Teams can version control their skill libraries in a shared repository, run PRs on new skills just like code, and share them across projects. A skill built by the backend team to handle database migration edge cases can be adopted by the DevOps team the moment their tasks match the same triggers. This is how OMC evolves from a personal productivity tool into an organizational knowledge platform. And this organizational context, your skills, your routing rules, your deep interview outputs, all of it feeds directly into the final piece, building your complete OMC workflow end to end, which is exactly where we are headed next. Let's stop talking theory and walk through a real feature request from start to finish using OMC. Imagine your product manager drops a vague ticket. Add user notification preferences. Most developers would just start coding, and that's where things fall apart 2 sprints later. Instead, you fire deep interview first. OMC's interviewer agent asks targeted clarifying questions. Push or email, per event or digest, user level or org level overrides. You get a spec in minutes, not meetings. Now you hand that spec to team mode. The architect agent breaks it into subtasks. The coder agent implements the preference schema and API endpoints, and the verifier agent runs tests and catches the missing migration file before it ever hits your branch. Finally, you inject a custom skill, your team's house rule for notification payload structure, so every generated handler matches your existing event bus contract without you writing a single correction prompt. The entire loop, from ambiguous ticket to reviewable PR, runs in under 15 minutes. That's not a demo trick. That's the actual workflow OMC is designed for. But here's the part that surprises most teams. The handoff between agents is where hidden bugs either get caught or get shipped. And the next scene shows you exactly how to read that handoff to know which one is happening. Now that you've seen the full workflow, the next question every developer asks is, which mode do I actually reach for? Getting this wrong costs real money in real time. Here's the decision framework. If the task is ambiguous or spans multiple systems, always start with deep interview, then route to team mode. If it's well-defined and repetitive, autopilot is your lowest friction path. Ralph is the right choice when you have a linear, dependency chain build where order matters strictly. Ultrawork is reserved for genuinely complex, multi-file refactors where you need maximum reasoning depth and cost is secondary. Pipeline mode is your go-to when you're composing OMC into a larger CI/CD automation. Think scheduled jobs or webhook-triggered workflows. The key variable is not just complexity, it's your cost budget and time sensitivity combined. A quick hotfix at 2am, autopilot. A greenfield service design, team mode with deep interview up front, a nightly code quality audit, pipeline. Print this decision tree and put it next to your keyboard. Seriously, it will save you from the most common OMC mistake, which is always defaulting to the most powerful mode regardless of the task. And speaking of mistakes, The recap coming up next crystallizes the 5 things from this entire lecture that you absolutely cannot afford to forget. 6 chapters in, let's lock in the 5 concepts that separate developers who get real leverage from OMC from those who just use it as a fancier autocomplete. First, pipeline stages are not cosmetic. They enforce a build contract where each agent's output is the next agent's verified input, which is what makes the whole system reliable instead of lucky. Second, orchestration mode selection is a skill in itself. Picking the wrong mode is the most common source of wasted tokens and wasted time. Third, smart routing is where the silent savings live. Most teams never configure it and leave 30 to 50% of their API budget on the table. Fourth, custom skills are your IP layer. They're how you encode your team's hard-won patterns so OMC produces code that actually fits your codebase instead of generic boilerplate. And fifth, deep interview is the single highest leverage action in the entire toolkit. 5 minutes of structured clarification prevents hours of rework downstream. If you only remember one thing from this lecture, make it that last point. The compounding effect of catching a misunderstood requirement before code generation starts is enormous. Now, knowing all of this is useful, but knowledge without action is just trivia. The final scene gives you the exact 3 steps to run today. Here is your concrete action plan. 3 steps, starting today, no setup paralysis allowed. Step 1, open the OMC GitHub repository right now. Star it so you can track changes, then read the custom skills documentation first. It's the fastest path from zero to something that actually fits your project. Step 2, take your next real task, whatever is at the top of your backlog, and run it through deep interview before you touch a single file. Don't modify the output. Just observe assumptions you are about to make silently. That experience alone will change how you work. Step 3, join the OMC community Discord linked in the repository. The team ships updates fast. The channel where developers share their custom skills configs is genuinely one of the most useful resources in the ecosystem right now. The developers who get ahead with tools like OMC are not the ones who read the most, they're the ones who run one real experiment this week. The entire AI agent landscape is moving toward orchestrated multi-agent systems, exactly like what OMC already does today. The teams building that muscle now will have a compounding advantage. It becomes very hard to catch up to 6 months from now. You have everything you need. Go build something.